Hi guys, so I'm recording here the solution of how to implement split using parallel prefix sum. So we are given a vector v of numbers. So in this case, the vector consists of 7 numbers: 17, 18, 22, 44, 7, 7, and 8. All right. And they're just arbitrary numbers. Now, in practice, of course, this vector will be long. It could be billions, maybe even trillions of elements long. And each of these elements is marked with either 0 or 1. All right. And the job is to move all the elements marked 0 to the front of the array while preserving their relative order, and move the elements marked 1 to the end of the array while preserving their relative order. Now, this comes up in a number of number of computations. One example, of course, being the convex hull problem that I showed you. But here we are just interested in understanding how the split operation itself works, and it's an interesting academic exercise in its own right. Okay, so let me just write the answer to what we expect it to be. So in this case, the elements that are going to be moved to the front of the vector are 17, 18, you see, because they're marked with 0, 7, and 8. And the elements that are going to be moved to the right of the vector are those marked 1. And remember, we are preserving their relative order, so they will be moved as 22, 44, and 7. Okay, now, so basically what we want to do is, and yes, 22, 44, and 7. Yeah. So remember, so when performing the split operation, essentially what we want to do is to determine for each of the elements marked 0 to which position in the answer array, which I'm marking with a yellow vector, should that particular element move to. So for example, how do we decide that 17 must move to the 0th position? 18 must move to the 1th position. 22 must, 7, the 7 here, marked here, is going to move to the 2nd position, and 8 here is going to move to the 3rd position. And likewise for 22, 44, and 7 when it comes to the 1 flags. So once for each element we have, once for each of these elements we know which index in the answer vector that particular vector element is going to move to. Now it's a very simple matter of programming threads to pick up that element and then just deposit it into the particular position in the answer vector. Okay, so that's not difficult. What is difficult is finding the index position into which each particular element of the given vector v that it must move to. All right, so how do we do this? So first we do it in 2 steps. The first step is finding the indices of all the elements marked 0. Okay, and later on, as you can see below, I'm going to find the indices of all the elements marked 1. Okay, so let's start off with the vector v. Now, I've just copied that here along with the flag vector given to us. All right, now in order to find the indices of all the elements marked 0, we are first going to invert each of those flags. All right, so that means 0 becomes a 1, 0 becomes a 1, 1 becomes a 0, 1 becomes a 0, 0 becomes a 1, 1 becomes a 0, 0 becomes a 1. And then we perform a plus pre-scan. When you do a pre-scan, so when you do a pre-scan for the plus operation, the first element is always the 0 element. The 0 element, remember, is the additive identity for the addition operation. Okay, now having decided that we're going to do a plus pre-scan, and you'll see we'll get the right indices in just a moment, we execute it. So having gotten 0, we are now going to do 0 plus 1, that's 1. 1 plus 1, that's 2. 2 plus 0, that's 2. 2 plus 0, that's 2. 2 plus 1, that's 3. 3 plus 0, that's 3. This one at the end plays no role and we just completely ignore it. All right. And that's what we do with a plus pre-scan. If it were just a normal scan, the arrows would move in a different direction, as you will see in the next section. But let's keep that aside for now, and let's just pay attention to the indices that have been generated for all those elements that had that were marked with the flag 0. All right. So let me use the orange color, for instance, and let me circle the flag with the corresponding index. So the flag that was marked with a 0 here got an index of 0, which means the element 17 that I've marked with the downward arrow here is going to be moved into the 0th position, as you can see from the answer that I generated above for us. Similarly, the element 18, which was also marked with a 0, is going to be moved into the 1th position of the answer array. You see, here we go. 18 was moved into the 1th position. And now similarly, 7, which was also marked with a 0, moves into the 2nd position. You see, 7 here was marked went into the into the 2nd position, or the position labeled 2. And the final 8, which also had a flag of 0, went into position 3. So you see, this went into position 3. And so I didn't circle 17 because, well, okay, just to be consistent. So 17 went into position 0. All right. So you see so after you do a plus pre-scan, the elements which had the 0 vector will move into index positions 0, 1, 2, 3 respectively in the answer vector here. Okay, which indeed is the case that is. So now let's look at finding the indices of the elements marked 1. This is, again, it's a little weird, but it's not too dissimilar from this. So again, we have to do something weird with the flag operation, with the flags array. So given the flags array here, what we are going to do is execute the plus scan. Remember, it's the plus scan, not the plus pre-scan. We are going to execute the plus scan in the reverse direction. Okay. Now, let's see. Now, remember, it's a plus scan, not a plus pre-scan. So let's see what the direction of the arrows is. Again, this was done in class, so so you can refer to those notes as well. So what happens here? Let's see. 0, we start off with 0. Why do we start off with 0? Because it's the first element here. Okay, so this is our 0. And now what we do is notice the direction of addition. The direction of addition is 0 plus 1 is equal. Oops, what happened here? Oops, just 1 second. Yeah. So 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 0 is 3. And 3 plus 0 is 3. Okay, I want you to compare that again. I mean, just ignore the reverse direction for now, but compare that with the way the pre-scan arrows went. The pre-scan arrows went vertical and then down to the left. In scan, you go to the left and then you go down. Right? So just make sure that you keep that. It's a very elementary thing to know. I mean, you should know it by now, but hopefully it's clear now. So anyway, so what we get is a bunch of numbers. All right. 3, 3, 2, 1, 1, 0. What we do now is consider the length of the vector. Now, in this case, the length of the vector is 7, right? There are 7 elements in the vector. 1, 2, 3, 4, 5, 6, 7. So what I'm going to do is I'm going to subtract each of these numbers from 7. So as you can see, 7 minus 3 is 4. I should probably erase this I don't want to confuse you with lots of arrows here. So as you can see, 7 minus 3 is 4, 7 minus 3 is 4, 7 minus 3 is 4, 7 minus 2 is 5. That doesn't look like a 5, so let me just erase that. That looks like 5. That's better. 7 minus 1 is a 6. 7 minus 1 is a 6. And 7 minus 0 is a 7. Okay, so we've got a bunch of numbers: 4, 4, 5, 4, 4, 4, 4, 5, 6, 6, 7. Sounds like a phone number. And let's look at all the elements in the vector v that were marked with a flag 1. Okay, so let's see. 22 was marked with a flag 1. And what index position have we generated? We have generated index position. Let's see. We have generated index position 4. For 44, we have generated index position 5. For this 7, we have generated index position 6. That means in the answer vector, 22, 44, and 7 are going to move into positions 4, 5, and 6. And as I said again, it's a trivial matter to program threads to move each of those elements into the final destination vector, now that you know the indices that those elements the indices that those particular elements are going to move into the new vector of the new vector. So as you can see, 22, 44, and 7 have moved into positions 4, 5, and 6. Okay, so 17, 18, 7, 8 were moved into positions 0, 1, 2, 3. We computed that at the end of phase 1. You see the circle, this here where we circled 0, 1, 2, 3 in red. And the flags marked 1 were moved into positions 4, 5, 6. And we circled them with yellow. All right. So now we have, well, I mean, that's the answer, right? So now we know for each element, whether it was marked with a 0 or a 1, which position in the new array it must be moved to. And that's about it. There's nothing really fancy about it. All right. But it was a nice description of how the parallel prefix sum is used to implement this very important operation, which you often see in parallel algorithms. So I hope that clears it. Thank you.